This video is about graphing polar equations. As always, begin by reading through the textbook and taking careful notes, but now consider the following highlights for this topic. We'll begin by recalling that from our development of polar coordinates, which was a previous topic, we know the following equations. We know that x equals r cosine theta. We know that y equals r sine theta. And we know that r squared equals x squared plus y squared. Hopefully those look familiar, again, based on the previous topic. And now, or actually even then in the previous topic, we will substitute these equations to convert some basic polar equations into rectangular form so we can graph them using familiar algebra. So we're going to start with these basic ones because they allow us to use our algebraic experience, and then we'll go extend beyond those a little bit as well later on in our examples. Let's begin by recalling also graphs of circles or lines from algebra. So to be specific, the general form of a circle is given as x minus h in parentheses squared plus y minus k in parentheses squared equals r squared. And this has center h comma k and radius r. So that may or should look familiar, but if it's a little rusty or forgotten, here's a little reminder of it. And then, of course, according to some lines, we have slope-intercept form, which is y equals mx plus b, pretty familiar form, with slope m and y-intercept 0 comma b. Point slope form, which is y minus y1 equals m times x minus x1, with the x minus x1 in parentheses there, and has slope m and contains the point x1 comma y1. Of course, one advantage of point slope form is that the point does not have to be an intercept, just any point. And then vertical lines, which are not functions and don't fit either of those forms, could be expressed as x equals a, which is when it passes through the point a comma 0 on the x-axis. And then also we will graph more complex polar form equations, but using a graphing calculator, as you'll see in the examples below. Let's jump in with some examples. Our first one says, express the polar equation in rectangular form and sketch its graph. All right, so we're given, in this case, a polar form equation. We want to convert it to rectangular form, which we've been doing. That was our previous topic. But now we also want to sketch a graph. The polar form equation given is, in this first example, theta equals negative pi over 2. Now, we've actually done one like this recently where we first recognize where that angle or arc would take us. So if we go just back to a basic coordinate plane, you can imagine a unit circle on it if you like, but the point is we know where this angle would be showing up. Negative pi over 2 means you're going clockwise. So from our initial side of the positive x-axis, if you're rotating clockwise, which would mean downward into quadrant 4, if you're going negative pi over 2, that would take you to the bottom of the axes, the lower or negative y-axis territory. Now, if you're rotating in that direction, again, you can imagine maybe standing on the origin and just pivoting yourself. So now you're looking straight downward. We've already kind of seen how this works, where r, the radius, is not specified in this equation. So I'm going to note this, r not specify. What does that mean? Well, that means it could be anything. So what we discussed previously was that, what if r was 1? Well, then in pointing this direction straight downward, your graph would be extending 1 unit down if r was 1, right? But what if r was negative 1? Well, then it would be extending in the opposite direction. Remember, negative radius means you just simply go backwards from where you're facing after rotating. Or what if r was 5 or negative 27 or anything, right? R is not specified, so we have to assume it could be anything, which means if you do all of those possibilities, you're either pointing downward or upward upward being a negative radius, downward being positive since you're already facing that direction after rotating negative pi over 2. Any of these combinations would then produce all the way up forever and all the way down forever on the y-axis, which is exactly the graph. So what we could say is the graph of this in rectangular form is just the vertical line x equals 0 because of what it means for theta to be negative pi over 2 and r to be not specified, which could be then anything. Let's go on to a next example. Our second one begins as r equals 6 sine theta. So again, that's given in polar form, and that's familiar. We're seeing r or theta. We need to convert it first to rectangular form and then try to graph it. Now, we've seen some tools or tricks of doing this in our recent topics. And for this one, we're going to have to use one of those. I'm going to copy the equation down just to have some space to work with it. R equals 6 sine theta. And then you may recall us doing this trick where you multiply both sides by something. In this case, if we multiply both sides by r, some convenient things will happen. Again, the more you see these tools or tricks, the more quickly you'll think of them. So on the left side you have r times r now, which is really just r squared. On the right side you have 6 times sine theta times r. Well, we're going to rearrange that just for convenience to make it 6 times r sine theta, right? A multiplication is commutative. You can switch the order of those factors there with no problem. What's nice now is we're seeing some familiar things. So on the left side with r squared, as we recalled above, we know r squared is really just x squared plus y squared. That's just a direct substitution or replacement there. And then on the right side, we have 6 times r sine theta, but we know that r sine theta is y, as recalled above as well. So we really have this equal to 6y for our rectangular form. Now, we have just x's and y's, which is good news, but it's not in a very familiar graphing form for us in algebra. We have x squared plus y squared equals 6y. It's not quite linear, and it's not even quite in the familiar conic section format of maybe a circle or some other conic section type graph, an ellipse or something like that. So we're going to do a little more algebraic work on this one. Namely, we're going to get all the terms on the same side first, and then use another algebraic method to get this in a familiar format. I'm going to subtract 6y from both sides. This will get everything on one side. And so we'll now say we'd have x squared plus y squared minus 6y equals 0, since we moved the 6y term over to the left side. Now that still isn't super helpful. However, we can use this by doing what's called complete the square. Complete the square. This is an algebraic method or skill that we're going to bring back in here by review. And it's going to help us get this in a familiar form. So if I have x squared plus y squared minus 6y, so maybe you've seen this method, you probably have at some point, but it could be forgotten. What we're going to do to complete the square is add a mystery term that will complete this trinomial of y variables that we're kind of seeing in our equation here. So we had y squared minus 6y. We're kind of missing, though, a term that will help us complete and make this a square term, as you'll see shortly. But if I'm adding some mystery term to the left side of this equation, then of course you have to add the same thing to the right side, just to keep things balanced. So I'm going to put a plus blank on both sides to help complete the square. Now, what you may recall from completing the square is that there's a specific term we want to add here, and it's b over 2 squared. That may sound familiar if you've recognized some of this algebra. B over 2 squared. And b comes from the middle term of our y variable trinomial that we're kind of working with here to try to complete the square. So when we see y squared minus 6y, then the minus 6, that's our b. So what that means is b squared, or b over 2 squared rather, is really negative 6 over 2 squared. So let's rewrite this as x squared plus y squared minus 6y like we already had, but now I'm going to say plus, and then it's really negative 6 over 2 squared. And we're going to have to add that to both sides. So on the other side where we had 0 originally, we'll say now plus, same thing, negative 6 over 2 squared. And yes, we'll simplify that here. So we'll make this now x squared plus y squared minus 6y plus negative 6 over 2 is negative 3, and then square it, and you get positive 9. So we're going to say plus 9 for that mystery term, which means on the other side, same thing, 0 plus 9 would be just 9. Now, why do we do this? Because this creates the general form of a circle that we were reviewing above. So we're going to rewrite this one more time as x squared plus, here we go, we can factor now this perfect square trinomial, which was created through our process of completing the square. It's really now y minus 3 in parentheses squared. You can double check the factoring on that. If you expand y minus 3 times y minus 3, you should get these three terms that we got here produced recently in the previous step. And this is called completing the square. Why does this matter? Because now we're looking at a general form of a circle, according to what we reviewed above. So this is now an easy thing to graph, where we find the center of our circle. Remember, we recalled that's h comma k. Well, h is 0 because there's nothing inside the x in parentheses. So we'll say 0 for the x center, and then the y coordinate, remember it's x minus h and y minus k. That means k would be positive 3. The center coordinate, or the y coordinate for the center, would be 3. And then this is equal to r squared, which means if it's equal to 9, that r is 3. So all we have to do is plot the center point, which is 0 comma 3. So we'll go up 1, 2, 3 points. And then from there, we have to extend a radius of 3 in every direction. So that means up, down, left, right, 3 units all around. We'll just kind of mark this by hand on here. It's hard to draw a circle nicely by hand, just do your best. We're going to put these points down here and then draw a circle that touches hopefully all those outside points that extend out 3 units from the center of 0, 3, producing then the final graph of our equation, which started in polar form, was converted to rectangular form, and now is here. I'm going to make some space here to box this in. There's our final graph, the circle. Now, I will also add that it's convenient to convert this to rectangular form because it turns into this familiar graph, which is a circle. We'll see this happening in some of these cases, but it's also possible to graph in polar form by making a table. You may see this in some textbooks where they'll actually consider theta as this input variable, maybe r as the output variable, and you can make a table of theta comma r, or even r comma theta, and you can create points that you can then plot on a graph to produce it as well. So there are other ways to come up with this, but when you can convert it to a familiar rectangular form, I think this is probably the simplest way. All right, let's try another one. This next one begins as r equals negative 2 cosine theta. So again, we're given this in polar form, and actually you'll notice some familiarity or similarity with this one and the one we just did, but this one is using cosine instead of sine. So let's do the same kind of thing. If you multiply both sides by r to get this in a usable form, let's see, then this would produce r squared on the left side equals negative 2r cosine theta on the right side. Again, that's just multiplying by r on both sides, as we did in the previous example. Now if we replace our familiar things, like r squared is really x squared plus y squared, and then on the other side, so that's equal to negative 2 r cosine theta, now that's just an x. You'll notice a similar setup from the previous problem, but this time there's a lone x variable instead of a lone y variable. Lone meaning it's just a single variable, it's not squared, but its squared counterpart is somewhere else in the equation, right? So you have an x squared plus y squared on the left side, now equal to a negative 2x. Well, if we follow the same strategy we did last time by bringing the variables on the same side, so if I add 2x to both sides of where we are now, this would give us then x squared plus y squared plus 2x on the left side equals 0 on the right side now. And for convenience, we would like to notice that we have an x squared and an x term on the left side. That's a hint that we're probably going to need to complete the square for the x's. This time we have a y squared, but no single y variable, which means we don't need to complete the square on the y's. Kind of like in the previous problem, we did complete the square on the y's, but not on the x's. Again, it's just depending on what you have in the equation. So for this one, we're going to do the same kind of thing where I'm going to rearrange these and use the complete the square process. So I'm going to rewrite this as x squared plus 2x. I'm just putting that term next because we're going to use it as part of these x terms to make a trinomial that's a perfect square. But then plus this unknown mystery term as of yet. So we have x squared plus 2x plus blank. Now we still have the y squared term on the left side. We're going to keep it there as just plus y squared. And then that it's equal to 0, but then plus blank, we have to add the mystery term to both sides. What's the mystery term? Well, it's b over 2 squared. Just like last time, this is the standard term we're going to add when completing the square, as seen in algebra. So let's do this where, again, b, running out of space here. Let's see, when b is actually the coefficient of the x term in this case, that's just a positive 2. So we're going to make this x squared plus 2x plus, if b is 2, then 2 over 2 is 1, when squared would be 1. So it's really x squared now plus 2x plus 1 plus the y squared we had over there on the left side. But then that's equal to, on the right side, 0 plus, well, b over 2 squared we just decided was 1, so it's going to be just equal to 1. Now this creates a perfect square, which we can factor. So x squared plus 2x plus 1 is the same thing as x plus 1 in parentheses squared. That accounts for now completing the square and creating something that's usable in rectangular form. And then that's now also plus y squared on the left side equal to 1. Well, again, this is in a standard form of a circle where the center would be h comma k. In this case, h is negative 1. There is a number in with the x. We use the opposite of the sign of that number we see there, since it's a minus in the formula for it. So we have x plus 1, which is really x minus negative 1, which means h is negative 1. K, of course, this time is 0 because there's no number in with the y in parentheses here. And the radius is equal to 1, since on the other side we have 1, and that's supposed to be the radius squared. So 1 squared is 1, which means the radius is 1. So now we can put this on a coordinate plane graph pretty simply. We have a center at negative 1 comma 0. We'll go left 1, put a point there for our center. The radius is 1, which means you would extend 1 unit in each direction, up, down, left, right. We'll just do our best to sketch this in by hand and hopefully get a somewhat reasonable looking circle. Circles are not always easy to draw. Just do your best with it. Show your work is the main thing. And there's our circle. So we have a graph now produced from the rectangular form. Again, you could, like I mentioned, make a table to graph a polar form equation. You'd have to do a little bit of input-output with the trigonometry, using unit circle values and then finding the cosine of them in this case, or in the previous problem, finding the sine of those theta values that are just hopefully typical unit circle values. You can do it that way in a table, or when convenient like these, convert it to rectangular form first and then just produce the graph that way. Actually, all three of these examples have done that. So that's just a convenient method when it applies. Now, let's keep going to get some other examples going. This next one says use a graphing calculator to graph, and then it's given the equation r equals cosine of, in parentheses, theta over 2. And then notice it says more. It says choose the domain of theta to make sure you produce the entire graph. Now, what in the world is that talking about? We're going to explore this a little bit, including an introduction to how a calculator can actually be used here. So let's take out our TI-84 Plus graphing calculator and do just that. If you're using the default setup on any of these calculators, you press the Y equals button in the top left corner and likely get a screen full of Y variables like y1, y2, y3, and so on. And you've likely used this in algebra where you can create or input functions, like y is a function of x, and then it'll graph it for you, right? Well, in this case, we're actually using polar form, which is not going to use that. we're rather going to switch the calculator mode in order to accommodate polar form. So I want to explore this and play around with it first before we get into some of the details of this specific graph and how we ensure we have the entire graph. So to get the right mode on the calculator, we're going to press the mode button, which is, again, kind of the upper left region of the calculator next to the second button. If I press mode, your screen opens up with a bunch of options on it. You may have used this kind of stuff before. If you go down to the row that says FUNC, and then it says PAR, and then POL, and then SEQ. So this is a mode row we're going to want to edit. It's probably in function mode by default, but we want to shift it over to polar form. So if you scroll over to the POL and then press enter, it'll now put the little highlighted cursor on that form, which shifts the entire mode of the calculator. So now if I hit the Y equals button, same button we pressed earlier, notice this time the screen is populated not with Y1, Y2, but with R1, R2, R3, and so on. So this is evidence that you're in the right mode or shifted into this polar form mode. Now, let's first start by graphing the function given and then see what it may look like and how we may need to account for this entire graph issue here. So I'm going to start by noting that our equation is r equals cosine of theta over 2. Well, we have r1 equals built into this screen for y equals, but in polar form mode. And that means I'm going to type in the cosine to match our function, and then it opens up a set of parentheses in which I want to put theta over 2. Now, if you just press the variable button, that typically gives us the x when we're in function mode. When I press that same button, notice this time, it throws a theta in the screen automatically instead of an x. That's because we're in the different mode. Now, we want theta over 2, so I'll divide that by 2, close parentheses, and there is the original equation or function given in polar form, now put in the calculator. Now, we're not just going to press the graph button. Let's go do a couple things. First of all, we're going to look at the window to see what this even sets up for us. If I press the window button, you'll notice even these things changed with the mode change here. So now we have theta min and theta max and theta step. Those are not usually theta unless you're in this polar form mode. Notice it says theta min equals 0 and theta max equals, and then it says for the max 3.1415926 and ... That's likely pi, right? That's an approximation of pi. And so it's likely that this is by default, or at least maybe the way I had it set up or used previously, going from a theta min of 0 and a theta max of pi. Okay, just take note of that for a second. Now, if I take a look at the graph of this by pressing, let's do this, zoom, and then we want to zoom in a little bit on this one. Let's do a zoom 4, which gives us just a standardized kind of closer zoom window. We've done zoom 4, zoom 6, those kinds of things, right? You'll notice a weird curvy looking graph that seems to be somewhere in quadrants 1 or 2, and it doesn't quite look like a circle, but it also seems to kind of curl back in on itself in an interesting way. Kind of moves up through quadrant 1 into quadrant 2 and then kind of curls back toward the origin. So that's interesting, but that's so far what we're seeing in our graph. Let's mess around with the window for a second to see if we can edit even this a little bit more. So if I press the window button, where it says theta max, remember that was listed at what is probably pi. Let's change that to 2 pi, just to see what happens. I'm going to go ahead and edit the theta max by typing in 2 and then pressing the pi button, so second, and then you see pi above this little caret button here. Notice now our theta max is 2 pi. If I do the same graphing window by hitting the graph button, notice what happens. So we see a part of what we saw the first time, where it kind of goes up through quadrant 1 and 2 and then curls back down the origin toward the origin, but this time it kind of keeps going. It like curls around again and goes further into quadrant 2. So obviously we're seeing more of the graph when we adjust the domain or the window of our graphing utility here. That's getting into what this question is asking, which is choose the domain of theta to make sure you produce the entire graph. Okay, so the question is, have we done that, right? Is this the entire graph? Well, we may not be sure of it at this point. We're going to do a little bit of algebra to verify or be more sure whether we've produced the entire graph. And let's do that here next in our space provided. Now, since we're working with periodic functions, these trig functions, the question really that we're asking ourselves is the following. We'll put it this way. How many times should or must theta rotate 2 pi, that's one full circle, to start repeating? That's the question we're kind of thinking in our minds here. So we have a periodic function, which means we have, cosine, as we know, is periodic. You can input theta values that go all the way around the unit circle, and then at some point they start repeating, right? Based on the period of the function. We've seen this plenty of times. So we know that about a periodic function, and our question here is, how many times must theta rotate through a full circle, 2 pi, to start repeating the graph? Now, to do this or find this algebraically, we're going to begin by taking our function, which was cosine of theta over 2. Now, I know it was r equals that, right? That's going to produce the graph. But we're going to take what r equals and say, when then would that equal? And then so we'll say cosine of theta over 2. That was our original function that r equals, right? When would that equal cosine of... Now, if it's going to rotate a certain number of pi over 2's, we're wondering when will that produce the same result as theta plus 2n pi all over 2. Okay, so in other words, this 2n pi thing, let's see, I'm going to note this here on the side. So this 2n pi we're talking about, this is a multiple of 2 pi, where n is just some variable, n is an integer, let's say, and so you're multiplying 2 times some number, it could be 2, 3, 4, 5, whatever, times pi. This is going to produce some multiple of 2 pi, or whatever n is of that. So if we do this kind of setup, what we're saying is that's going to start repeating on itself, because you're adding some multiple of 2 pi, which is going to start repeating with the period of our graph. So what we'll do is more algebra to get this going. I'm going to say that this expression, so we had equals cosine of, and then I had in parentheses a fraction whose numerator was theta plus 2n pi all over 2. And we're going to split that up to make this theta over 2 plus 2n pi over 2. So that's just a little fraction arithmetic there. I'm just splitting up the fraction. It already has then a common denominator of 2. We have cosine of, in parentheses, one fraction as theta over 2, plus another as 2n pi over 2, 2n pi being some multiple of 2 pi, right? So our question is, when will this happen? When will it be a first multiple of 2 pi? Well, think about this for a second. You have 2n pi over 2. It's almost there. The question is, what n value could I substitute in for n and produce a multiple of 2 pi? Well, think about this. What if n was 1, right? Or what if n was 2? Well, in those cases, you'd be plugging in those numbers for n. If n was 1, then you would just get 2 times 1 times pi for that term, that second term here, all over 2. But then notice the 2's would cancel because you're dividing by 2 there, and that would leave you just with 1 times pi, which is not a multiple of 2 pi. So that makes us sad. That doesn't do it. So what about if n was 2? Well, then we would have 2 times 2 pi all over 2 for, again, the second term we're looking at. Then in that case, we have a couple 2 factors on top. One of those would cancel with the 2 below, giving us a result of 2 pi. But that is a multiple of 2 pi. In fact, that's the first one because it's 1 times 2 pi. So turns out that when n is 2, what happens is that this second term produces a value for our function equal to the original. So in other words, you take theta over 2, which was the original input. If I add 2 times n times pi all over 2 to it, where n is 2, then I'm really adding a multiple of 2 pi, which will produce then the same result. So what we're going to say here is that when n is 2, then 2 times 2 pi, which is what we would be adding to the original. I'm going to highlight that in the same color here. That's where that came from. That's what we're adding to this numerator of our original input. That would produce the same result. So what does that mean? Well, it means when we have 4 pi, then we get the result we want when we're adding in that numerator 4 pi. So what that means is that our domain for this function, in order to repeat on itself, would be from 0 to 4 pi. Now, what does that mean for our calculator? Well, we're going to go back to the calculator. Go ahead and pull that out. And this time we're going to go back to the window. So turn it on. Hopefully everything is still typed in there. We don't know yet quite if we've produced the whole graph, but if we go back to the window, and this time use a theta max, we had put in, I think, 2 pi. We're going to try 4 pi this time, which is what we just calculated here. I'm going to type it in 4, and then second, and then the pi button to get 4 pi. Now I'm going to hit graph and see what happens. You'll notice we see the familiar graph, but then it keeps going, and it seems to loop all the way back to where it started in this graph, which produces this kind of curly looking, cool looking graph. So that's how we can verify that the graph now has done one full repeat and will now start overlapping itself. If you produce, or if you set the window to be even higher, so we did 0 to 4 pi, watch this. If we do 0 to 8 pi, which would be just doubling that domain, and hit the graph button, it'll produce the same thing we just saw, and then it seems to just stop doing anything, but that's actually because it's now overwriting itself. It's just simply repeating, right? These are periodic functions. It's producing the exact same graph. You just can't even see it moving because, well, it's overwriting itself exactly. And so that means now we don't want all of that extra space. We only want the domain that would produce the entire graph as specified in this question. We did the little algebra here to figure out that's 0 to 4 pi. So that's all we need, and we can graph it. Now, in this case, we're not going to draw the graph by hand. So I'm going to say here, C graph on calculator. Sometimes drawing some of these trickier, complex-looking polar graphs by hand can be a nightmare. So we're not going to always draw those by hand, but we did produce it on a calculator, and we produced the domain that we needed in order to verify that we had the entire graph. Let me just clarify one thing before we move on that may not have been super clear. So it's when we're talking about adding a multiple of 2 pi, right, which we just did all this algebraic work to find when n is 2, we get there. Well, that was actually applying to what we were adding to the original function. So notice, let's see, it's actually this second term where we ended up with 2n pi all over 2 after splitting the fraction. That was what we were adding to the original input, which was just the theta over 2. So it's when that thing we're adding becomes a multiple of 2 pi. That's what we want the first time of to find, right? And that's where we kind of said, well, what if n is 1? Nope. Now it's just pi. That is that piece you're adding. What if n is 2? There we go. So when we were getting those simplified results, we were doing so using the expression for that second piece that we were adding into the function. Okay. Another way to do these sometimes is to do a little bit of guess and check on the calculator. You can plot, you can just kind of guess it like maybe a domain of pi, see what the graph looks like, increase it to 2 pi and so on. Find out how long it takes to get somewhere where it's repeating, so at least you can see it twice. But algebraically, there is a more robust approach, which we just demonstrated here. All right, let's do another one. This time we're going to use a graphing calculator to graph the following equation. It's given as the left side has a set of parentheses containing x squared plus y squared, and those parentheses are raised to the power of 3. And then that on the left side equals, on the right side, 4x squared y squared. All right, now it says first convert the equation to polar form. Well, we've been doing that in recent problems and topics, so I think we'll be able to do that just fine. Again, recalling our equations to do so. And then we'll even talk a little bit about the domain and what might make sense for this one. Now, let's start by recognizing that on the left side, we had x squared plus y squared in parentheses, and that was all cubed. Well, that's the same thing as r squared, isn't it? So since we know that x squared plus y squared really is r squared, and on the right side we have x's and y's as factors, we know the equations for those as well. Let's go ahead and substitute all this stuff in. So that means on the left side, in parentheses, we really just have r squared cubed, simply replacing x squared plus y squared with r squared. And then on the right side, we have 4x squared y squared, but we're going to replace x with r cosine theta because we know that to be the case as a direct replacement. So I'll have now 4 and then in parentheses r cosine theta, but then that is squared. Those parentheses are squared. And then next to that, in the same kind of way, for replacing y, we'll have r sine theta in parentheses, and then also squared since it was y squared, just like the x squared. All right, so what we have now is a polar form equation, which we can tell because we have all r's and thetas. And we'd like to simplify this a little bit more. So let's do a little bit of exponent simplification first. On the left side, we have r squared cubed. Well, that's really just r to the 6th. That's just using algebraic exponent rules where you multiply those powers together. And then also using those rules on the right side, we can simplify that to be 4, which was already out in front as our coefficient there. And then since we have a product inside each of these parentheses, r times cosine theta or r times sine theta, with a product, you can apply the squared or power outside the product to each of those factors inside. This, again, just goes back to some algebra. So we'll write that as 4 r squared cosine squared theta r squared sine squared theta. And we could simplify this even a little bit more. Let's start over and keep the r to the 6th on the left side. But on the right side, notice we have a couple r squared factors that we could multiply together. So we'll do that and write the right side as 4 and then r to the 4th. That's the product of those r squareds. And then cosine squared theta, sine squared theta. And notice at this point, you could, or we could divide both sides by the higher power of r. And so if we do that, if we divide both sides by r to the 4th, or I'm sorry, the lower power of r to the 4th on both sides, then of course the r to the 4ths cancel on the right side. On the left side, they reduce. R to the 6th over r to the 4th would be r squared. Again, just using algebra exponent rules there. So that equals, on the right side now, we have 4 cosine squared theta sine squared theta. Next, if we remember some of our, well, let's do another little algebraic trick here. If we take the square root of both sides of our equation, notice that we have on the right side a bunch of factors. That's kind of a hint that taking the square root of the whole side wouldn't be such a bad idea because you're allowed to apply a square root to multiple factors that are next to each other, which means we're left with r equals, on the left side, the square root of r squared we can write as just r. On the right side, we're going to say then the square root of 4 is 2, the square root of cosine squared is cosine, and the square root of sine squared is sine. So we have now r equals 2 cosine theta sine theta. But let's recognize that there's actually an identity lurking here. Let's see, I'm going to recall, because it's maybe been a little bit since we've used this, but we know that sine of 2 theta equals 2 sine theta cosine theta. So that's an older identity for us that we could actually recognize as happening right here. in this very equation. Of course, the sine and cosine are kind of flipped in the order we might be used to seeing them. I think we wrote it as sine, cosine. This is cosine, sine in terms of the order, but that's not a big deal. That doesn't change anything. So we'll write this as really r equals r equals sine of 2 theta, just using that direct identity replacement here with where we were. And that is the simpler form of our polar equation we want. So r equals sine 2 theta. Let's go ahead and take out our graphing calculator to see if we can now produce a graph of this one. And to do so, we've already had it converted here in polar form. We have r equals sine of 2 theta, and we have our calculator in polar form, as demonstrated in our previous example. So we're going to go ahead and type our equation in now. We'll say r equals, and then I'm going to type in sine, and then we want 2 theta in the input. So we're going to type 2 and then press our variable button, which throws a theta in there, now in polar form. Close parentheses, and that's our function. Now, we've messed around with the window before. Let's do this again. If I go to the window, okay, so I have it set at a theta min at 0 and a theta max at, looks like pi. If we graph this, remember, this may or may not produce the full graph. Let's take a look at it. If I press zoom, let's do a zoom 4, I suppose, to zoom in a nice window. We see this kind of butterfly looking thing, or maybe a half butterfly. Let's try to get a closer look at this shape just to be able to identify clearly what's happening. We can zoom in a little bit more by pressing the zoom button up near the top, and then option 2 says zoom in. So if you go down, scroll down to it and then hit enter, then it takes you back to the graph but doesn't do anything. You have to hit enter again to apply it. We'll do that, and there it is. So now it's a closer look at this, again, kind of like a half butterfly or flower looking thing. Some of these graphs get pretty elaborate or intricate looking and kind of pretty in design. Just kind of fun to note, right? You'll notice though, like we don't know exactly if we have the full graph or not. So let's do just the window guess and check method on this one. If I hit the window button, we're going from 0 to pi. What if we went from 0 to 2 pi? So let's try this now, where the theta max is typed in as 2 and then the pi button. So 2 pi is my theta max. I'm going to hit the graph button again, which will take us back to the same window. Aha, turns out now we get this symmetrical, again, flower or butterfly looking thing that goes through all 4 quadrants. Now, we want to produce the graph of this, and that is it, right? Now, might we have more here that we're not seeing? Well, as we saw before, if you can identify when the graph starts overlapping itself by reproducing the same values for r, then you can usually spot when it may or may not be the full complete shape. So you could do that even just with a guess and check. I'll demonstrate that here. If you press the window button, so we went from 0 to 2 pi, you could try something like 0 to 3 pi and see if you get anything different than what you just saw. So I'll try that here. I'll set for the theta max 3 pi and then hit the graph button again, and it produces, sure enough, the exact same result. Now, remember, it might be producing it 1.5 times, but then overlapping itself for more of it. That's fine. All we're trying to do is produce the graph.